What role do equations play in physics? Can you describe the motion of the world with a single equation? Physics is the study of how the universe works, exploring matter, force, energy, motion, and space-time. Then, what is the relationship between physics and mathematics, the language we use to understand the laws of nature? These two fields are like mirrors reflecting each other, and throughout history, they have remained closely connected and inseparable. From the perspective of mathematics, physics is a source of new ideas that never stops flowing. Just as number theory studies the properties of integers and geometry explores figures and space, physics has often served as an important starting point for the growth of mathematics. At the same time, physics needs mathematics as a language to express the laws of the universe precisely. It is like a shared language that helps us translate complex natural phenomena. Among these, equations are the key tools for uncovering the laws of physics. For example, when we throw a ball at an angle, it travels through the air in a curved path and then falls to the ground. If the force, angle, or weight of the ball changes even slightly, the landing position becomes completely different. We can analyze the motion of the ball through many experiments and describe these relationships with equations. Now, let us think. How can we find out how the starting conditions affect the result? An equation is the tool that connects what we already know with what we do not yet know. We use a system of equations to analyze the motion of a curved path and organize complex movement into a single formula. It is like scattered points coming together to form one curve. In this way, equations have played an important role in developing the core theories of physics. Let us start with classical mechanics. Classical mechanics explains how objects of visible size move. Newton organized the basic principles of motion through the laws of inertia, acceleration, and action and reaction. He also showed that, in the end, we need to solve equations to understand motion. What happened in electromagnetism? Electricity and magnetism were once thought to be separate phenomena, but the British physicist Maxwell unified them into one. 4 partial differential equations, called Maxwell's equations, explain electricity, magnetism, and even the nature of light. They became the foundation of modern electrical civilization. In other words, invisible forces can be described with just a few equations. Now let us turn to time and space. Einstein explained gravity not as a force, but as the curvature of space-time. He focused on the fact that the speed of light is always constant and developed the theory of special relativity. Here, the key idea remains the same. We always need equations to express the laws of nature accurately. When we enter the very small world we cannot see, things become even more fascinating. Quantum mechanics studies the microscopic world smaller than atoms. In this world, the laws of classical mechanics no longer apply in the same way. So we use mathematical tools such as linear algebra, group theory, and differential equations to describe the world in entirely new ways. We need a more precise language to understand the invisible world. Why do physicists express complex ideas through equations? The first reason is that mathematics has no limits. From the secrets of nature to everything we can express, mathematics goes beyond physics and can be used in any field. Like a toolbox with no end, it can grow as much as needed. The second reason lies in the way mathematics works. Mathematics begins with definitions and axioms, then uses logical proof to decide whether a conclusion is true or false. If the starting point is accurate, the result we obtain is also reliable. Because of this structure, mathematics can be both highly abstract and very powerful. The key concept here is abstraction. Abstraction is the process of finding common structures within complex phenomena. When things that once seemed different are understood within a single framework, we can understand it more deeply. From this perspective, equations are not just tools for calculation. They are a shared language that connects many natural phenomena and a window that helps us understand the complex world. In a way, it is natural that equations, the essence of mathematical abstraction, have become the central tool of physics.